everyone, welcome back. I'm Domingos. I'm also known as DMA and appreciate when I'm called DMA. So today we have this equation exercise to solve. X to the power 2i minus 2 times x to the power I plus 2 equal to 0, where I is imaginary unity defined as square root of negative 1. Okay, if we look at our equation, it has the characteristic of a quadratic equation. So let's solve considering it as a normal quadratic equation. So let's start by finding the value of the determinant, which is defined by b squared minus 4ac, which b is the coefficient of the x term, but in this case x to the power I. So we're going to have minus 2 squared minus 4a, in this case is the coefficient of the quadratic term, and the c is the constant. So this is going to be 4, this is 8, 4 minus 8 will be negative 4. So if we find the square root of the determinant will be square root of negative 4, which is equal to square root of 4 times square root of negative 1. Square root of 4 is 2, and square root of negative 1 is our imaginary unity, which is I. Okay, now let's find the value of x. We know that our variable in this case is x to the power I, which will be equal to, according to the formula, is minus b square root of the determinant of delta over 2a, which is in this case will be equal to, what is my b? Is 2. So if this negative will become positive, plus or minus square root of this expression, 2i over 2 times a is 1, then will be 2. If we refactorize 2 here, and 2 here, we're going to have 1 plus or minus I, because if we factorize 2 on top, it will simplify with the 2 in the denominator. Okay, now we have plus or minus, so we have to find the value of x for the plus first, and then for the negative. Okay, so first case, then let's use the positive one. We're going to have x to the power I will be equal to 1 plus I. Okay, how do we calculate here? We can apply ln, natural logarithm, both sides. So if we apply it, we're going to have ln of x to the power I equal to ln of 1 plus I. Okay, this I is the exponent of the argument of this ln can come this side at the back. So I can come here, multiply. And if it's multiplying, can go that side dividing. So this can be here to be 1 over I. Okay, can be 1 over I. So we can have ln of x. It's 1 over I. We can multiply the numerator and the denominator by I. So we're going to have 1 over I times I over I, ln of 1 plus I. Okay, now we're going to have ln of x being equal I times I. It's I squared, which is negative 1. Negative 1, I divided by negative 1 is minus I. So we're going to have minus I times ln of 1 plus I. Okay, now we have this expression. This minus I, it's multiplying this ln, can come at the exponent of the argument of the ln. Okay, so we're going to have here, this can be rewrite as 1 plus I to the power minus I. And we know if ln of A is equal to ln of B, this implies that A is equal to B. Okay, if that is true, then we can apply it here. So that means that x1 will be equal to 1 plus I to the power minus I. So we could live in this form, but it's not that beautiful, and it seems like we don't know some other tricks. So why don't we transform the base, which is a complex number, also in terms of the exponential form of a complex number? So if we do that, we will need to find first the module, which is the magnitude of this complex number, the base, and also its angle. So that means the magnitude, it's going to be square root of 1 squared plus 1 squared, because we know magnitude, it's the square root of the real part squared plus the imaginary part squared. So this is going to be equal to square root of 2. Finding the angle theta, we know that it's the inverse tan of the imaginary part, which is 1, and over the real part, which is 1. Sine and cos, they are positive in the first quadrant, right? So that means this angle belongs to the first quadrant. So that means it's 45, which I can write in radian, pi over 4 plus 2 kp, because it's not the only angle. Yeah, it is pi over 4 when k is 0, when there is no revolution. Okay, So in one revolution, we just substitute the value of k by 1 and 3 and 2 and so on. Okay, now having that, then we can say now that x1 can be written as this expression in terms of exponential form. We know it's the magnitude times the Euler to the power of the angle, which in this case is pi over 4 plus 2kp times the imaginary unity. All this is only the base, so all this to the power minus I. Okay, so that means in this case x1 will be equal, applying the power rule, when they have common exponent, we can separate each one with the exponent. So we're going to have square root of 2 to the power minus I times this I, when multiplies this I, will be I squared. Because of the negative, will be positive. So that means we're only going to be left with Euler to the power pi over 4 plus 2kp, which k represents the number of revolutions. Okay, so k belongs to the integer set. Okay, now we have to find the value of x2, which is definitely using the negative. But all this approach that we did can be applied to the second x, which I can call 2. So x2, it's the same. If we check all the approach that we did up to here can be applied, so we can say x2, it's going to be 1 minus I to the power negative I. And we can find the magnitude of the base and also its angle, the same way we applied here. So the magnitude will still be square root of 2, because the magnitude will be the real part squared plus the imaginary part squared, so which will produce square root of 2. Okay, now the angle I can call angle alpha, not use theta as well. Again, if I find the angle alpha, then we'll have an inverse tan of the imaginary part, which is negative 1 over 1. So when I see that, I can realize that imaginary part is negative and real part is positive. So that means angle lies on the fourth quadrant. So that means our angle is 315 degree, which is 7 pi over 4. So we can say plus 2 kp, where k represents the number of revolution. So that means apply the same principle here. We can write in this form, this exact form. So x2 will be the magnitude times Euler to the power 7 pi over 4 plus 2 kp I, all this to the power negative I. So x2 will be square root of 2 to the power negative I times Euler to the power 7 pi over 4 plus 2 kp, where k belongs to the integer set. So this is how we should solve this problem. Okay. So if you enjoy, leave your like, your comment, subscribe, and most importantly, share with your friends.